Refraction through a lens. Lens. A lens is a transparent refracting medium bounded by either two spherical surfaces or one spherical surface and the other surface plane. Kinds of lenses. Convex or converging lenses. Double convex, plano-convex, and converging meniscus. Concave or diverging lenses. Double concave, plano-concave, and diverging meniscus. Technical terms related to a lens. Center of curvature. The center of the sphere whose part is the lens surface is called the center of curvature of that surface of the lens. Since a lens has two spherical surfaces, so there are two centers of curvatures of a lens. They are represented by C1 and C2 in the given figure. Radius of curvature. The radius of the sphere whose part is the lens surface is called the radius of curvature. PC1 and PC2 are the respective radii of curvature of the lens in the given figure. Principal axis. It is the line joining the centers of curvature of the two surfaces of the lens. C1, C2 represents the principal axis in the given figure. Optical center. It is a point on the principal axis of the lens such that a ray of light passing through the point emerges parallel to its direction of incidence. It is generally represented by letter O. Principal foci. A light ray can enter the lens from either side, therefore a lens has two principal focus, one on either side of the lens. These are known as first focal point f1 and second focal point f2. First focal point. For a convex lens, the first focal point is a point f1 on the principal axis of the lens such that the rays of light coming from it after refraction through the surface of the lens become parallel to the principal axis of the lens. For a concave lens, the first focal point is a point f1 on the principal axis of the lens such that the incident rays of light appearing to meet at it after refraction from the lens becomes parallel to the principal axis of the lens. Second focal point. For a convex lens, the second focal point is a point f2 on the principal axis of the lens such that the rays of the light incident parallel to the principal axis after refraction from the lens pass through it. For a concave lens, second focal point is a point f2 on the principal axis of the lens such that the rays of light parallel to the principal axis after refraction from the lens appear to be diverging from this point. Focal plane. A plane normal to the principal axis passing through the focus called the focal plane. A lens has two focal plane since it has two focus. First focal plane and second focal plane. Focal length. The distance of focus or focal point from the optical center of a lens is called its focal length. A lens has two focal lengths, first focal length and second focal length. Formation of an image by the lens. Characteristics and location of images for a convex lens. Case 1. When the object is at infinity, that is, U is infinity. Characteristic and location of the image formed. The image is at the focus or in the focal plane. On the other side of the lens, it is real, inverted, and highly diminished. Application. In this manner, a convex lens is used as a burning glass or a camera lens. Case 2. When the object is beyond 2f1, that is, U is more than 2f. Characteristics and location of the image formed. The image is between f2 and 2f2 on the other side of the lens. It is real, inverted, and diminished. Application. In this manner, a convex lens is used as camera lens when the object is not very far to be photographed. Case 3. When the object is at 2f1, that is, U is equals to 2f. Characteristics and location of the image formed. The image is at 2f2 on the other side of the lens. It is real, inverted, and of the same size as the object. Application. In this manner, a convex lens is used in a terrestrial telescope for erecting an inverted image formed by the objective lens. Case 4. When the object is between f1 and 2f1, that is, f is less than u, which is less than 2f. Characteristics and location of the image formed. The image is beyond 2f2 on the other side of the lens. It is real, inverted, and magnified. Application. In this manner, a convex lens is used in cinema and slide projectors. Case 5. When the object is at f1, that is, u is equals to f. Characteristics and location of the image formed. The image is at infinity, that is, at a very far distance on the other side of the lens. It is real, inverted, and highly magnified. Application. In this manner, a convex lens is used in the collimator of a spectrometer to obtain a parallel beam of light by placing the source of light at the focus of a convex lens. Case 6. When the object is between lens and the focus, that is between O and f1 or u is less than f. Characteristics and locations of the image formed. The image is on the same side and behind the object. It is virtual, erect or upright, and magnified. Application. In this manner, a convex lens is used as a reading lens, that is, a magnifying glass or a simple microscope, to form a magnified virtual image of a tiny object. Characteristics and location for image for a concave lens. Case. When the object is at any finite distance from the concave lens. Characteristic and location of the image formed. The image is between the lens and the focus on the side of the object. It is virtual, erect, and diminished. Application. In this manner, a concave lens is used in spectacles for short-sighted persons. Lens formula. The equation relating to the distance of object u, distance of image v, and focal length f of a lens is called the lens formula. It is same for both convex and concave lens. 1 by v minus 1 by u is equals to 1 by f. This is the lens formula. Linear magnification. The ratio of the length of image perpendicular to the principal axis to the length of object is called linear magnification. Linear magnification m is equals to length of image I upon length of object O, that is v upon u, power of a lens. The deviation of the incident light rays produced by a lens on refraction through it is a measure of its power. Power of a lens in diopter is equals to 1 upon focal length in meters. Application of lenses. The objective lens of a telescope, camera, slide, projector, etc. is a convex lens which forms a real and inverted image of the object. Our eye lens is also a convex lens. It forms the inverted image of the object on our retina. When our eyesight weakens, we use spectacles having either a convex or a concave lens. A magnifying glass is a convex lens of short focal length fitted in a steel or plastic frame provided with a handle. A concave lens is used as the eye lens in a Galilean telescope to obtain the fine erect image of the object. A single convex lens usually forms colored or blurred image due to the chromatic aberration. Therefore, a combination of concave and convex lens is used to overcome such a defect. In a collimator of a spectroscope, convex lens is used for obtaining a parallel beam of light.